Now that we've learned our different forms of energy and how they can transfer from one form to another, let's look at some moving objects and see how energy creates their motion. So here we have three situations. The ball is above the ground, the ball is moving towards the ground, and the ball is about to hit the ground. It goes from stop to moving faster. At the top, do the list. It's off the ground, so it has gravity. It's not moving, so no kinetic. It's not stretched or compressed, so no elastic energy. As it moves towards the ground, we still have gravitational energy because we're off the ground, but now we have kinetic energy because we're moving. If the ball was halfway between the top and bottom position, kinetic and gravitational energy would be half and half. But because it's higher than halfway, gravitational energy is higher, kinetic energy is smaller. This explains why it's moving slower at the top and moving much faster at the bottom. In this case, at the very end, the only thing it's doing is moving. You could argue that it's off the ground a little bit, so there's a little bit of gravity. This wind-up toy has a compressed spring inside of it. So it has elastic energy stored, it's moving, so it has kinetic energy. As it moves forward, it slows down, so there's less kinetic energy. The elastic energy goes down as well because the spring releases some of its energy in order to make the toy move. This energy goes into dissipated energy. The kinetic energy dissipated. The elastic energy turned into kinetic energy and dissipated. The dissipated energy is caused by the toy rubbing against the surface, creating friction and creating sound. At the very end, it stopped. All the elastic energy has turned into sound or friction, so it's all dissipated. It's stopped. You could also, because it says it's on a table, have a wedge of gravity in all three pie charts, but that amount of gravity would not change. We've observed this situation before of an object being thrown in the air and coming back down. The only thing acting on it is gravity, so we're going to see some trends. At the very beginning, it's moving, so we're going to ignore the gravity. It's being thrown up in the air. It was just launched, so it's only moving. That's the only thing it's doing. The second position is above the halfway point, so we have more gravity than kinetic. And we know that it's less kinetic because as it moves towards the very top, it slows down. At the very top, vertically, it's not moving. You could say there's a small sliver of kinetic energy because it's moving horizontally, but I'm going to ignore that for now. On the way down, halfway, we have half gravity, half kinetic energy. It's moving and it's off the ground. It's halfway between its highest point and its lowest point, so half of its energy is gravity. The other half has to be kinetic. And then right before it hits the ground, it's moving just as fast as it was launched. So now it is moving towards the ground. It's not on the ground yet, so it's just kinetic energy. Now we have a ball rolling. It's pushed, so at the very beginning, the only thing that it's doing is moving. All of its energy is kinetic. The faster it's moving, the more kinetic energy it has. It starts to slow down, so we have less kinetic energy. It slows down due to friction, so we have less kinetic energy because the rest of that kinetic energy dissipated. It was turned into thermal energy from friction. It was turned into sound energy as it rolled along. And then it comes to a stop because it's out of energy. All of the kinetic energy dissipated through thermal and sound energy. So we're left with just that category of energies, dissipated energy. This is another scenario where even though it's moving horizontally, we're going to assume that it was just bouncing straight up and down. It's off the ground at the beginning, it's not moving, and it's not stretched or compressed. So it's only gravity. Do the checklist every time. When it hits the ground, it becomes compressed. That's why if you look, the ball goes from round to oblong. When a ball hits the ground, it squishes. This is why footballs, basketballs, etc. have air. It's a lot easier to compress that. So we have elastic energy. When it hits, it makes a collision. That collision creates thermal energy with friction. That collision creates sound energy as it smacks the ground or bounces. Imagine the sound of a basketball bouncing on the ground. That's where that dissipated energy goes. That energy, think of it like a fuel tank. We used that dissipated energy. It wasn't destroyed, but we used it for something useless. So that piece of EDIS stays the same. Now it's back up to its second highest height. It's not moving except horizontally a little bit, but right now it's not as high up because its gravitational energy is smaller. This is why the ball could not bounce back up to its original height. The dissipated energy took some of the original gravitational energy, making it so it could not transfer all the way back up to its original height. It's kind of like a car that runs out of gas 2 blocks before it gets to the destination. Then it hits the ground again, becomes compressed again. The E-dis now gets bigger because we had another collision. More of that energy was dissipated, more of it turned into thermal energy, to sound energy. It's not lost, but it's no longer useful to us. It turned into something else. Then it bounces back up. That same size chunk of E-dis exists. It doesn't get bigger when it's in the air because there's no more collisions. The gravitational energy is smaller each time it bounces up because each time it hits the ground, it dissipates more and more energy. The very last pie chart of this would be all E-dis. All that gravitational energy was dissipated into the universe, so now we're left with just a ball by itself. Here we have a chunk of clay or object on a spring. It's launched up. It starts with elastic energy. You could argue it's off the ground a little bit, so there might be a little gravity in there, but basically we have elastic energy. The spring is compressed. That spring releases, launching the object in the air. Now it's more than halfway up, so it's going to be more than halfway gravity, less than halfway kinetic. When it's all the way up, it's 100% gravity because we know objects reach a top point, stop for a moment, change direction, and then come back down. In this scenario, we started with a chunk of clay. At the very beginning, it's not moving, so no kinetic. It's not stretched or compressed, so no elastic. It's off the ground, so it's only gravitational. As it moves downward, we're halfway between its highest point and the ground, so it's halfway gravitational, halfway kinetic. I know it's kinetic because it's moving. The arrow tells me so. When it hits the ground, even though it squishes because it's clay, it does not squish, it does not compress with the intention of decompressing or springing back up. In this case, it just splatters. Imagine the sound of taking a chunk of clay, throwing it at the ground. You'd hear the noise. It would create friction when it hits the ground. And in fact, it can create some vibration in the ground. It dissipates all its energy. It stops dead the second it hits the ground.